Welcome you all to the Research Spark YouTube channel. So this is the second and the last session of the unit third, feedback amplifiers and oscillators. So in this session, we are going to discuss the stability analysis of the feedback circuit, then the oscillators. So we'll see the principle of oscillations, was a classification of oscillators, and some examples, that is RCSC and the crystal oscillators. So first, how will know that whether the feedback system is stable or not? So if you wanted to check the stability, first check the gain, that is the amplification factor with the feedback, so that exactly it will be the A divided by 1 plus of beta A. Beta is your feedback factor and A is the amplification factor, that is gain of your amplifier. And also the beta A is called as the T, that is open loop gain, that is loop gain also. And now if suppose T is less than 1, if phase difference is 180, then the system is stable. And also if it is greater than 1, if with the phase 180, then the system will be the unstable. Simply the denominator term, that is A divided by 1 plus of beta A, must not be the negative, otherwise the system will be the unstable. Now here is the example. So single stage common emitter amplifier. Here see, you can see this is the feedback based amplifier only, which contains the feedback, that is RL, and you can see the emitter circuit, common emitter circuits. So what is our objective? Our objective is to find out the AF, that is the gain exactly. So if gain is like A and B, that is the gain product, if it is lesser than the one, then it will be the unstable. So initially if the gain is higher, but if you are going to have the multi-stage, then the gain will keep on reducing, and the product of gain and the feedback factor will be the lesser. In that case the system may be the unstable. So first find out the gain. So here you can take the help of the AC analysis, and if you will solve, then you will get the gain, that is GMR pi into RC divided by RC plus RL into 1 divided by 1 plus SRC. So here just draw the board plots, like both plots we are trying, because we wanted to draw the exactly the gain, that is how much gain is varying corresponding to the frequency. So here you can see the board plots for the single stage amplifier, magnitude and phase difference. So with the help of this one only, you can see the gain is decreasing, like after F1, that is the cutoff frequency for the particular this BJT based amplifier circuit. Similarly, we can have the two-stage amplifier circuits, where the gain, that is the AI, will be your AI divided by 1 plus of J of F1. So you can also calculate this gain similar, like whatever that we have found for the single stage. So now here gain will be, you can see the gain is reducing with the gain divided by 1 plus square root of f by f1 square whole square 1 plus f by f2 whole square, and the phase will also will reduce tan inverse f by f1 plus tan inverse f by f2. So phase will keep on reducing, and also your gain will keep on reducing. So now if we'll see the board plot in the right side, then now your gain is reducing after f1, that is minus 20 dB, and after f2 it will be minus 40 dB, because now the minus 20 dB because after the f1, and minus 20 for after f2. Similarly, now in the phase shift also you can observe. Now at the 90 you can see the phase difference is the it's repeating after 90. So now we'll have the lesser phase difference of 45 degree. For multi-steps, like for 3 steps, you can see the board plots and the gain. So gain will keep on reducing, and your gain, the board plots for your gain and the phase difference you can see here. So with the help of this one, we can say that the system will be the stable or unstable. So again, if it is lesser than the minus 1, then this will be the unstable. Now, if it is not lesser than, like suppose if it is equal to the 1, means the denominator, if it will be the 1, denominator will be the 0, means AF will be the A divided by 1 minus 1, means simply if denominator will be 0, then this time what will happen, the AF will be the infinity. So this is also, the being used to design the oscillator. So simply, this is also called the Barkhausen criteria. So T will be the minus of 1. So in actual oscillator circuits do not have any input signals, because like without input signals, even the noise only will be used to amplify the signals, and it will help to generate the some particular frequency because of oscillation only. So in oscillation circuit, beta is a principal portion of the loop gain that is dependent on the frequency. So beta, our objective will be to find out the resonance frequency, because this will be used to generate the some frequencies. So that is why the oscillator is important. So the basic principle is to, the because of this property of the amplification factor and noise is there. So because of that only, now the signals will oscillate, and it will, because the T is equal to minus 1. So now amplification will be the infinite. So there are the different types of the classification of oscillator based on the nature. Here you can see harmonic oscillators, then the relaxation oscillators, so LC, RC, and the crystal oscillators. Then based on the components used, then there will be the phase shift oscillator, wine breeze oscillators, Hartley, Colpitts, and then based on the feedback, you can Hartley, Colpitts. So you can check all these. So just check the some important types of the oscillators. So left one is the RC, phase shift oscillator. So here phase shift, that is RC is containing in the series. So if you'll find out the resonance frequency, then it will be the frequency, that is omega is equal to 1 by square root of 6 into RC. And similarly for wine bridge, just see the circuits here. Now in wine bridge, R and C is in the parallel, and the resonance frequency is simply omega is equal to 1 by RC. Since R and C are same for both the parallel in series for both, if it is different, then the frequency omega naught will be the 1 by square root of R1 C1 R2 C2. Similarly, we have the two more different configurations of the oscillator. So first one, just check it. This one is the Colpitts oscillator. So in that, like if we'll check the configurations of your crystal oscillators and the other oscillators, then these are the very similar oscillators. So here we are going to use the two capacitors, one inductor, and having the resonance frequency omega naught is equal to 1 divided by square root of L C1 C2 divided by C1 plus C2. For Hartley oscillators, again, just similar things. Just replace your capacitor with inductor and inductor with capacitor. Now it will becomes the Hartley oscillator. Here, omega naught will be the 1 divided by square root of L1 plus L2 into C. So what is the advantage? Like whatever the frequencies you wanted to generate with these different oscillators, you can manipulate the values of the L and C, and you will get the corresponding frequency. So lastly, so let's discuss about the crystal oscillator. So crystal is nothing. This is the piezoelectric materials which is being used to, such as a quartz, so which will exhibit the some frequency. It will have the some, that it will produce the some force, and that is why the frequency, because of the some input applied voltage. And so how much the frequency, how much it will have, so you can calculate. So first you can replace it with the some, the stop circuits, that is containing the RLC circuits only. So it is equivalent to that RLC only. CS and CP is nothing, that is the capacitance in series and the parallel only. And so lower one is the circuit, that is the resonance, like the oscillator circuit only. So it is very similar to Colpitts and Hartley. Just replace the, the inductor with your piezoelectric materials with and then only crystals only, and then you will get the crystal oscillator. So the resonance frequency again, so ZS says here you can calculate. So it depends on the CS and CP. And so again, because of the CS and CP, so frequencies between the resonance frequencies will vary from your FS and FP. FS is frequency in the series, and frequency in the parallel. So in order to calculate Fs and Fp, you must know the values of the C and Ct. So how will you calculate? Let's see here. So Fs will be calculated is equal to 1 divided by 1 by twice pi LC square root, and Fp can be calculated using the Fs into 1 plus C naught by C. C naught is the shunt capacitance of the crystal. So that's all in this session. So you should try to do the some more exercises based on this. So I have discussed in very short because of the the time limitations, and also you should also we'll see the some the some sessions in the next unit. So in the next session we will talk about the unit 4th, where we will see the different applications of the linear ICs. Particularly we will check the IC741 and the different applications. Thank you for listening. If you have any problem, please drop your comments.